So in this section, we're going to be talking about unusual values and outliers. So kind of the extremes that we wouldn't necessarily think about. All right. So before we do that, let's talk about a z-score. So a z-score is defined as the distance that a data value is from the mean in terms of the number of standard deviations. So it's the distance that the mean is from, or the distance any data value is from the mean in terms of standard deviations. And ultimately it's used for a standard normal distribution. So this is a great way that we can compare multiple sets of data. So if you have heights of men and heights of women, right? Men and women typically are differing heights, right? Men are typically taller. So this is a good way to compare between two different data sets. It's another way to compare literally apples and oranges. So the way that we do it is that we want to make sure the mean is 0 and a standard deviation is 1. So it should be pretty easy. Mean is 0, standard deviation is 1. So let's figure out what this formula should be then. So basically, if we have so we have like IQ scores, for instance. And IQ scores have a mean, so this is, remember, population mean of 100 and the standard deviation of 15. Well, if we draw a normal standard deviation, right, we know right there in the center is going to be the mean, which is 100. One standard deviation above is going to be 100 plus 15, which is 115. Two standard deviations above is going to be adding another 15, which is 130. On the other end, if we're going to try to do one standard deviation below, right, we're going to do 100 minus 15, which would be 85. If we do another one, that's going to be 70, right, so on and so forth. So for z-score, basically we want to do it to where we can translate all of it to where instead of these really high numbers, the mean is just 0. Instead of one standard deviation above being 115, it's just going to be 1. Two standard deviations is 2. Three standard deviations above is 3. And then on the bottom end, right, one standard deviation below would just be -1. Two standard deviations below would be -2, right? So this makes things a little easier on us. So basically, we need to figure out a formula where 100 gets turned into 0, where 115 gets turned into 1, where 85 gets turned into -1. So let's start with the first one. So 100 needs to turn into 0. So what could we do to turn 100 into 0? Well, we could subtract 100, right? So, okay, maybe the formula to go from data values to their z-scores is just subtracting 100. So let's try it with the other one. So 115, right? We said 115 needs to go to 1, right? Because it's one standard deviation above. So if we subtract 100, we end up with 15. Ooh, that is not 1. Okay, so what else could we do to turn 15 into 1? Well, some people might think that we could subtract 14, but remember, whatever we do, we're trying to get the same number, right? Or we're trying to find a formula that works for everything. So if we subtract 14 to 15, we do end up with 1, which is what we wanted, but then we would also have to subtract 14 to the original, right? Which is going to get us negative 14 and not 0. So subtracting isn't the way to go. So what's another way that we could get 15 to 1? Well, we could just divide by 15, right? If you divide by 15, you end up with 1. Now let's do it to the first case as well. If we divide 0 by 15, what do we end up with? Still 0. Okay, so this is looking good. Let's try one more, just to make sure. So let's try 70, right? So 70 is 2 standard deviations below, so the z-score should be negative 2. So we have 70 minus 100, because we said we got to subtract 100. We get negative 30, and then divide that by 15, and we end up with negative 2, which is exactly what we wanted, right? It was 2 standard deviations below. All right, so I think we got our formula. So, when trying to figure out the formula for the population, we're going to have x. X is your data value, so the original value that you're using. And we need to subtract, okay, so in this case we subtracted 100, but 100 might not always be the case. So what was 100 represented in this formula, or in this example? So 100 was mu. Remember, mu means mean. So in all these cases, we were actually just subtracting the mean. So you take your value, you subtract the mean, and then after we subtracted the mean, what did we do? So we subtracted 100 from each of these, and then we divide by 15. What was 15 in this case? 15 was sigma, right? Which is the standard deviation, the population standard deviation. So in all these cases, we first subtracted the mean, and then we divide by the standard deviation. So x minus mu, divide by the standard deviation. And that's it. So we figured it out. Now what about if it was a sample z-score? Well, it's going to be just the sample values. So the x is your data value minus, what's the sample mean? It's x bar, divide by the sample standard deviation, which is s. Yeah, so no matter what you do, the z-score is going to be x minus the mean, or we could even write it as your data value minus your mean, divided by your standard deviation. All right, so that's our formula. So notice, what do we know about positive z-scores versus negative z-scores? So what do positive z-scores tell us? So all they tell you is that it's just above average, right? The mean is 0, so it's above the mean, or above average. So if you have a positive z-score, you would be above average. And likewise, what would a negative z-score tell you? It would just tell you that you're below average, right? So you actually can have negative z-scores. They are below average. And typically what we want to do with the z-scores, we want to round to the nearest 2 decimals. There's a couple of cases where it's 3, but if you put 2, you should be fine for the most part. So we round z-scores to 2 decimals. Kind of like GPAs. All right, let's do our first example. So problem number 1 on our word problem handout. Determine whether the Boston Red Sox or the Colorado Rockies had a relatively better run-producing season. So the Red Sox scored 878 runs, and they play in the American League, where the mean number of runs was scored was 731.3 and a standard deviation of 54.9 runs. And the Rockies scored 845 runs, but they play in the National League, where the mean number of runs scored is 18.5 and a standard deviation of 61.7. So with comparison to their league, who actually did better? Now you might just say, oh, well, obviously the Red Sox did better, right? They have the bigger number. But if we notice, right, the mean is different. This mean is actually smaller than this one. So it's possible that the Rockies did better with their respective season and their respective league than the Red Sox did. So we actually have to check ourselves. So what's a good way that we could check ourselves? Well, if we knew, so we definitely know that the Boston Red Sox is going to have some version above average, right? And we know that the Rockies are going to be above average as well. So if we knew how far away they were, right, from the average, that could tell us who did better. So if this is the average of 0 for a z-score, and we knew how far away each of these were from the mean, from their respective means, we would be able to know who did better. So what that means is we need to know how many standard deviations away are each of these scores from their respective mean. And if you were paying attention, since the last thing we talked about was z-score, we're going to have to find their z-scores. All right, so Boston Red Sox. Remember, we have the z-score is, and is this going to be the population or is this going to be the sample? So this is of this mean and standard deviation is of everybody in this league, and everybody is a population. So we're going to use x minus mu divided by sigma. Make sure not to get these two confused, right? It's the value minus the mean divided by the standard deviation. So for the Red Sox, what was their value? How many runs did they run? So they did 878. So 878 minus, what was the mean for their league? So the American League, the mean was 731.3 divided by the standard deviation. So the American League standard deviation was 54.9. All right. When you subtract that out and then divide, you end up with about 2.67. So the z-score for the Red Sox is 2.67. So now let's check the Rockies. So again, this is going to be a population, x minus mu divided by sigma. X is the data value, so how many runs did the Rockies do? So the Rockies had 845 runs minus the mean, which is 718.3, divided by standard deviation, 61.7. So when we subtract first and then divide, we end up with about 2.05. So in this case, the person or the people who had the better run producing season is the one that has the higher z-score, right? It's the one that's further away from the mean in this case. So that would be the Red Sox, right? Red Sox have the higher one, and that's what you want in this case. So the Red Sox did better. All right. Let's do one more problem. So suppose Bob and Mary ran a marathon. Bob finished the marathon in 213 minutes with the mean finishing time for all men was 241 minutes and a standard deviation of 57 minutes. Mary finished the marathon in 239 minutes, where the mean finishing time for all women was 273, standard deviation of 52 minutes. So who did better in the race? So this one's a little trickier, but again, we want to see comparison with the z-score. So we have Bob and Mary. So We have the data value for Bob, which was 213, minus the mean of 241 divided by the standard deviation of 57. And when we look at that, we end up with about negative 0.49. Now, does it make sense that we have a negative number? Well, is Bob's time less than the mean? Yeah, so he would be below average on this case, right? Good. All right, as opposed to Mary. So Mary's data value is 239 minus the mean of 273 divided by the standard deviation of 52. And when we divide that out, we get about negative 0.65. All right, so here's a tricky question. Who did better in the race? So who did better in the race? I can tell you right now, the answer is Mary. Now, you may be thinking, well, wait a minute, Bob has the higher number, right? Bob's number is less negative, it's less than the whole. So shouldn't Bob be the one that did better in the race? Let's think about this. If you did better in a race, did you run more? Does your run consist of more time or less time? If you did better in the race than someone else, you should have less time ran, right? And since Mary's is the smaller number, Mary would have been on the path less amount of time than Bob, respective to her gender. Yeah, this is why this was a little trickier. So it just depends on what the actual problem is asking for. But in this case, Mary is the one who did better with respect to her gender. All right, I'm going to take a pause here, and I will make sure to upload video 2. So make sure to come back for part 2 of this.